Okay, welcome to the promised section on 8.4 potential energy diagrams and stability. First, let's talk a little bit about stability and how we call things that are stability or stable or what have you. So let's say we've got a bowl and a marble. And in the first case, we've got case one here, and the bowl is upside down, like you're going to dump your marble into the bowl, and the marble has enough energy to, it starts out, say, at this point here, and that energy, potential energy, allows it to drop down. But we're going to be doing it with friction, okay? So after some time, that ball is going to be pushed back and forth, and energy is going to take, friction is going to take energy out of the system, leaving us with the ball here at the bottom and a velocity equal to 0. How if we were to bump that ball with, say, this much energy transferred to it, it would again oscillate back and forth till it ended up back at the bottom. So any bump of ETM, energy of ETM, will contain the marble in its region. Okay. Now, let's say we're looking at number 2. Here we go, number 2 here. And we're going to bump that marble with energy, ETM. And in this situation, that marble will accelerate. So not only does V increase, A is not equal to 0, and not equal to. And so that's an ever increasing velocity and a runaway system. Okay, so marble goes away. Marble leaves the region. Leaves the region. And then third, we've got a marble, and we're going to give it a bump with ETM. If there's no friction, of course, then it'll have a velocity that it gets, and that velocity leads us to a kinetic energy that would be equal to ETM, and that also equals 1/2 mv squared. So we could figure out what that velocity is by saying that V equals 2 ETM over m square root. And then, of course, it's plus or minus, because if we bump it in the positive direction, it would go positive. And if we were to bump it in the negative direction, it would go negative. So that's our third. So there are names for these guys. The names. The name for number 1 is stable. So we're talking about stability here, so that makes sense, but it's stable equilibrium. Number 2 is unstable. Unstable equilibrium. And of course, number 3 is neutral equilibrium. Friction, you guys are going to hear me say this many times, but friction drives a system into equilibrium. So we have a system of a ball in a bowl, or a ball on top of a bowl, or as in 2, rolling over that backside of a bowl, or in 3 on a flat surface. That's our system, and friction is going to want to slow those things down. Of course, in 2, friction has no choice, no help. We're unstable, and our acceleration, if we're looking at it in a bowl situation, our acceleration really technically is g sine theta. But that bowl can only last for so long, and so that ends up turning into g, I guess, unless it's an infinitely large bowl. So that's our unstable situation. That's going to carry on and increase the velocity of the ball infinitely, right? Our stable situation, you can see how with friction, that's going to come straight to v equals 0 right away. Okay, like not right away, but pretty dang quickly, right? You won't have to wait long. In our neutral situation, this one's kind of almost the most interesting. And the neutral situation, friction not only slows us down, so we don't accelerate, okay, of course, because there's no, we'll talk about why there's no force, but we've got equilibrium, v equals 0 or a constant, and we have v equals a constant initially. V equals plus or minus square root of 2 ETM over M. That's initially, but the friction, what does the friction do? It comes in and it wants to decrease that even. So we end up with friction, we're going to end up with v equals 0. And we all know on a level surface, even a ball rolling, it might roll for quite a while, but unless it has wind at its back, its velocities, whether plus or minus, they're going to end up dropping to 0, and you'll end up with v equals 0. Okay? So these are the 3 possible conditions that you can have for equilibrium. We've got stable equilibrium, unstable equilibrium, neutral equilibrium. Okay, so great. Now let's start talking about the forces that are involved. And when we do, let's raise up a little bit more here. When we do it in a way of drawing out the potential energy. And I know it seems weird, But, okay, let's look at a mass. Oh, I didn't do that right. We want a mass, a block mass that's going to slide back and forth from minus x max to this point here, which is plus x max. And then right in the middle is going to be 0. And it's on a spring. Nice healthy spring. And that looks good there. So what is our potential energy for this situation? Our potential energy is U equals 1/2 kx squared. Here's the thing to learn. Oh, and then here's our mass of the block. If you wanted to draw that potential, I'm going to draw it right here. Here's a graph of our potential. It goes up as squared on both sides. So here's x, positive x, and here's negative x, and this, oh, wow, I am so good at drawing. Okay, that's our potential energy going up. Here we're at 0, x equals 0. Also, at that point, our potential energy equals 0. So, this is the curve. U equals 1/2 kx squared. If we come over here and we say this is x max, and that means this is minus x max, we can come up to this point, and that's the maximum of the potential energy that it can have. So that's U max, which happens to equal the total mechanical energy. Okay, so the other day we were in class doing our lab, and I wrote U equals minus kx, or I'm sorry, F equals minus kx on the board, and I said that's the derivative of this. It's true, but here's the equation, official equation right here. F equals minus the derivative of U of x with respect to x. This is how you get your force from your potential. So you have this potential, you can graph it as a curve, and if you were to look at it and you take the slope of it, or the gradient as it's called, you can take that slope, and that slope if you look at the minus of that slope, so minus the slope, that equals your force. Okay, so that's why they call it a gradient. The gradient of the potential is your force. Okay, so if we want to, at x max, let's do it. Let's find out what that force is. So we're going to take F equals minus kx, right? Because the derivative is 2 over 2 times k times x to the 1 leaves us with minus kx. So F equals minus kx, our force is equal to minus kx max. Okay, so that's what this slope equals at x max. If we were to go to the negative side, so this is the plus side. If we go to the negative side, we get minus k times minus x max, which gives us a kx max. So that ends up getting a slope minus our slope ends up being a force in the positive direction. So it's a minus slope at minus a position, and two negatives make a positive. So we end up with a force. The force at this point is going to point to the right, to the right, and this force is going to point to the left. Okay, that's how it's done. Now we're going to look at the next bit. Let's look at this next one. So we have a cool example. Love this example. This is the same example. Let's keep going up. We don't care about springs anymore. We want to learn about something cool. We're going to give ourselves this u of x. This is example 8.10, I think. Yeah, 8.10. And it's 2 times x to the 4 minus x squared. Okay? And I don't know if you guys have heard about the Higgs boson. They found it recently in 2018, I believe. I can't remember. Anyway, I should know exactly when it was found on the very day, and I'm not into those kinds of facts. But they call it, and I don't know if it's bad or cultural appropriation or I don't know, but they call it a Mexican hat potential. And I kind of think Mexican hats are pretty sweet. So I don't know. But it looks like that. Let's erase this unfortunate bit. Okay. And we have an inflection point. If you draw the curves correctly, you get an inflection point right around there. And this bit here is potential equal to 0. These are the most stable points. So we'll call this point 1, point 2. We've already talked about it, right? So you guys are familiar. What do we call this region right in here? What is this region? This is the unstable region. Because if you were to put anything here, if you had a ball or something, you put it right there, where's it going to go? It's going to go down, right? In a runaway type of situation, okay? Once we get to the stable region, we're good. And that stability goes technically to the moon. We just keep going up and up and up. We're going to have infinite stability in this way all the way. But we're not going to allow that, because we're going to say, no, right here is our total mechanical energy. And we are only going to be allowed at first to go from this point to this point. So that's all we can do. It happens to go through this stability, stable area, runs over the unstable area, comes back to stable, and goes back up and comes back down. So technically, with this much energy, it's a stable potential. The Higgs boson will want to be in one well or the other well, and goes back and forth in one or the other wells. But actually, it is a round potential, so it actually goes in a circle and stays this distance away from the center. So that's kind of an interesting case. But we're not going to be learning about the Higgs boson, unfortunately. We're going to be talking about simpler things. And we want to know what we're going to do. And I don't know if this is in the book or not. And I don't really care. I don't know what the question that they're asking in the book is. But my question is, first, I want to find, so let's write it out. A, what is the inflection point? Where we go from stable to unstable to stable, going from unstable to stable. Okay, what is that? So let's find it. What is that inflection point? You can see, there it is, okay? But how do we find that inflection point? It's not terribly hard. We're going to do the derivative of u of x with respect to x. The first derivative, we're going to just put this 2 out front. 4x cubed minus 2x. That does it. So what does that do for us? If we look to see where this is 1, because that inflection point is below it, or I'm sorry, closer to 0, it's less than 1. Closer to 0.2, it's more than 1. So we were looking for that to be 1. In fact, we're looking for it to be -1. And I don't want to deal with that, okay? Because we've got x cubed and x and all that stuff, and I just don't want to. But what can we do? We can take the double derivative. And that's going to give us 2 times 12x squared minus 2. And if we say that that equals 0, now we're cooking, okay? Because we're only going to have 2 spots that that's the case. And those are our inflection points. So if we solve that for 0, we're essentially solving this for 0. And 12x squared equals 2 gives us x squared equals 1 over 6. So x is equal to plus or minus the square root of 1 over 6. That is how far away from 0 this is. And it's plus or minus. This is the plus side. And here's the minus side. So that's minus 1 over square root of 6. All right. So good. We're not looking for the zeros. I don't care about those. We've got 3 zeros, and I don't want those. But I did want this. We kind of want this, 0.2. So how do we get 0.2? Well, that would be where the derivative is equal to 0. We're going to have the derivative equal to 0 in 3 places. 0.1, the most unstable point in the middle at 0, and 0.2. So really what we want is the derivative, the first derivative equal to 0, and that's this right here. So let's solve that equal to 0 to get points 1 and 0.2. Points 1 and 0.2. Okay, not too tough. Let's just say that it equals 2x. We're going to get rid of one of the x's. Like that. That's the 0x that we just got rid of. So that's the unstable, perfectly unstable x that we don't want. And that leaves us with x equals 1 over square root of 2. And that kind of makes sense. So 0.2 is at plus, we need plus or minus, plus 1 over square root of 2. And if we say we have this much energy, it's going to oscillate about 0.2 from here to there and back again. So that's what we're looking to do. And we want to know an estimate. If this was a perfectly symmetrical, which I don't think it is, an estimate of this point right here. Ooh, I just erased what I drew. An estimate of this point right there would be to take this distance and add it to this distance. There are other ways to find out what that is. What's a better way to find out what that point is? We can find out what u is at this point and come over and find out the equivalent u on that side and what the x is. That would be a good move. What is u of x at the square root of 1 over the square root of 6? let's rewrite what u of x is. Okay. So 2 times, all right, 1 over square root of 6. 1 over square root of 6. 6 square root, 1 over it, and then we want that to the 4th power. So 1 times, 2 times, 3 times. 0.028, and then we're going to subtract 6 square root, 1 over, and we're going to square that, and we're going to subtract off 0.167. And we're going to multiply it all by 2, and we get negative, which should be negative because we're below 0, right? We're down here, so below 0, negative 0.277 joules. We're dealing with SI units, meters, and all that other stuff, so this is in meters right here. Okay, so we've got minus 277 joules. What other places give us minus 277 joules? We have to solve that for minus 277 joules. I think here's what I think. Let's find out what our energy is at point 2. So our energy at point 2 is 1 over square root of 2. And then that difference will give us our total mechanical energy. So we're 2 times we're going to do it again. 1 over square root of 2 this time, though. So 2 square root, 1 over. 1 of them, 2 of them, 3 of them, 4 of them. And then, so we've got 2 times 0.250, and we're going to subtract off 2 square root. Enter. Oh, whoops, no, 1 over that. Multiply them together. And of course it's 1/2, 0.500. That makes sense. Great. That's 0.250. And we're going to multiply by 2, so that ends up being minus 0.500. I could have done all of that without a calculator, and I'm just not realizing it. Okay. So, nice, awesome. The difference is our ETM, so when we take a negative and subtract an even more negative, we get a positive. So our energy total mechanical is 0.222 joules. Okay? At the very bottom here, that's what our kinetic energy is. And depending on the mass of the particle or marble or whatever it is, we'll have that much velocity. What I really want to get to is the force at the different positions. So instead of looking at this position here, you can't see that. Instead of looking at this position, I think we should just stick with this position because I don't want to go into the rigmarole of finding out what that is. We're going to look at this one, and we're going to look at this one, and we're going to look at the force on those positions, okay? So what is the inflection point we found, okay? We found where is the bottom, and we want to know what is the force, so B, what is the force at the inflection point? Okay? And let's do the positive inflection point at the positive inflection point. We know what that inflection point is. It's 1 over the square root x equals 1 over the square root of 6. And technically, you guys want to know something? Mathematically, you're supposed to take the square root of 6 and multiply it by that and get square root of 6 over 6. That's how you're supposed to do it. Mathematicians, you're not supposed to have a root in the denominator ever. I thumb my nose at that. I'm just kidding. All right, that's here nor there. Let's do what is that force. We know what du dx is. So if the force is equal to minus du dx, then we can just write down it's 2 times 4, and then we're going to multiply that 4 times 1 over square root of 6 cubed. So 6 square root 1 over cube it. Is it cubed? Yeah, cubed. Okay, so that's 4 times, I'm just going to even write, I'm going to multiply by 4, so we don't have to screw around with even the 4. And we'll write out, that's 0.272 newtons. And we're going to subtract the same 6 square root 1 over 2 times negative, and we're going to add them together. Oh, let me just write negative 0.816 So our F is equal to, we need a negative right here, minus 2 times all of that. So let's add those together. 2 times it. That's minus a minus 1.09 newtons. F equals 1.09 newtons. And it's in the positive direction, which is perfect. We're pointing in this direction, which is perfect because we know that the ball or whatever it is going to be forced down, forced to go to the positive x direction. When it gets back up to this point, it's going to be going that way. You know what? I'm not going to figure out what that point is, but it doesn't matter. We can choose anything larger than 1 over the square root of 2. So square root of 2, 1 over that. 0.707 happens to be the sine of 45 degrees. Okay. Anything larger than that. So let's just pick 1. Let's pick at 1, wherever 1 is. We don't know where it is. Maybe it's this point right. Maybe 1 is right here. Could be. What happens at 1 in our equation? 1 is 1 minus 1. That's 0. Yeah, it's 1. Heck, we can't do 1, but we could do 8/10. We can do 1. All I really want to show you is that the force here at this point, this force is going to be pointing this direction. That's all I really want to show you. So I guess we can do that easily. If we use 1, so the du dx again, we'll do it in blue. X equals 1. What is the force? And not just what is the force, but what is the direction of the force? So u du dx equals 2 times 4 x cubed minus 2x. Making it easy on ourselves. We really want the negative of it, but if we figure out what that is at 1, we've got 4 minus 2 times 2 is 4, okay? And if we take the negative of it, because the force is equal to minus du dx, we take the negative of that, we get minus 4 newtons. And if we go back up, it's pointing in this direction. It's pointing in this direction, and it's a larger 4 newtons. So this curve must get steeper and steeper as it goes up, because it's the gradient, meaning the slope. So the slope already at this point, the slope is already 4 for this curve. Okay, I think you guys get it. the point is, for me, I would, when I do this and I ask you a question about it, I'm going to say, here's a point. Find me the force magnitude, but not just the magnitude. I want to know the magnitude, and I'm going to want to know the direction. Okay? So we found the magnitude of it and the direction, and we did the same thing for the inflection points on the curve. Okay? So that's the net nitty gritty there. Be able to analyze a curve. Look up the Leonard, L-E-N-N-A-R-D, I think, Leonard Jones potential. That one, I don't think I have it on the test, but that's a good one to look at because you can do the exact same stuff and practice. So if you're interested, look up the Leonard Jones potential and you can practice and do all the same stuff. Okay, have fun with that.